Alright, so let's look at chapter 6 here. And the first thing that we're going to look at is what we call rescaling data. So what we're going to do is just take that data, that's these 5 numbers, and just put them in a list. And we need to get all these statistics. So some of them are pretty easy to get. The min and the max are easy to get. So now what I'm just going to do is just do stat calc and 1 bar stats for list 1 and calculate, and I need x bar, which is the mean, that's 36, and I need the standard deviation s of x, which is 9.62. And then I'm going to scroll down. The min Q1 is 27.5, Q3 is 45, so my IQR is 17.5. The max is 50, we knew that. The median is 35. The range is 25, which is the max minus the min. Alright, so the min, the max, Q1, Q3, these are measures of position. Okay, those are measures of position. The mean and the median are measures of center. And the range, IQR, and standard deviation are measures of spread, or what we call variation. So now what we're going to do is we're just going to mark these. These are position, center, center, variation. And our original data set had a min of 25 and a max of 50, a mean of 36 and a median of 35, a range of 25, an IQR of 17.5, and a standard deviation of 9.62. So now the first thing that we're going to do is, this says to add 10 to our data set. So if you go and you have your list in list 1, if you go up to L2 and you simply put in second 1, which is list 1, plus 10, it'll take your data list and add 10 to it. So now what we got to do is we got to go and we got to get all of our statistics for list 2. So our new mean is 46, which is 10 more than the old mean. Standard deviation is still 9.62. That did not change. The min now is 35. The median is 45. Q1 is 37.5 and Q3 is 55. Those changed because those are measures of position, but the IQR stayed at 17.5. The max is now 60. And the range is now 60 minus 35, which is 25. So when we added 10, what changed? Well, measures of position changed. Q1 and Q3 also changed. Measures of center changed, but measures of variation did not change. Now the next thing they want us to do is to double it. So let's go into list 3, go up to list 3, and just do 2 times list 1. So now we took list 1 and we doubled it. So now let's go and stat calc 1 var stats for list 3, and we're going to calculate that. So our new mean is 72 from 36. I'm just going to move this over. New standard deviation is 19.24, so that doubled. Min is now 50. Q1 is 55, median is 70. So that doubled. Q3 is 90. Well, 90 minus 55 is 35. Well, the original IQR was 17.5, so the new IQR doubled. And then the max is 100. Well, 100 minus 50 is 50. Well, the original range was 25. So we doubled. Measures of position doubled, measures of center doubled, and measures of variation also doubled. Okay. Now the last thing we got to do is we got to do both. We're going to multiply by 2. So here we go. I'm going to do stat, edit, and I'm going to go to L4, and I'm going to say 2 times L1 plus 10. And now let's see what happens. I'm going to go to 1 bar stats, and we're going to go to L4. And my new X bar now is 82. So 2 times 36 plus 10. My new standard deviation is 19.24. So So what did it do? Well, it doubled the original standard deviation, but it did not add 10. So addition did not affect the standard deviation. My new min is 60. That's 2 times 25 plus 10. My new median is 80. That's 2 times 35 plus 10. My new max is 110. That's 2 times 50 plus 10. My new IQR is 100 minus 65, which is 35. Well, that's 2 times the original standard deviation, the original IQR, but adding 10 did not affect it. And my new range is 110 minus 60, which is 50. So, as far as multiplying and adding, we measures position and center, I multiply and add. But when I'm multiplying and adding, the addition does not affect measures of variation. The range only doubled. The IQR only doubled. The standard deviation only doubled. It ignored the fact that we add 10. So adding a constant changes measures of position and center, but not variation. Okay, so when we're talking about position, we're talking about min, max, Q1, Q3, so forth and so on. Center would be mean and median. Variation, there are 3 measures of variation. Those are range, IQR, and standard deviation. Okay? Multiplying a constant changes measures of position, center, and variation. So multiplying affects everything. Addition does not affect variation. So when combining addition and multiplication, addition affects position, that's our last case, and center, while multiplication affects position, center, and variation. What does that mean? Here in this case we multiplied and added. Okay, so what do we multiply by 2 and add 10 to? Well, all measures of position and all measures of center. But when we get down to measures of variation, the fact that we added 10 was irrelevant. All that happened was the original measures of variation doubled. They didn't care that we added 10. So we got to be careful when we get into cases like that. Okay. Alright, let's talk about normal models now. So a normal model is unimodal and symmetric. It follows what we call the empirical rule. That is really the 68, 95, 99.7 rule. Okay? And that means that about 68% of the values will fall within 1 standard deviation of the mean. So that would look like that. Okay. So for instance, IQ is modeled with a normal model of a mean of 100 and a standard deviation of 15. So the mean IQ score is 100, and this would be 115, and this would be 85. So 68% of people who take an IQ test will score between an 85 and a 115. 95% of the values will fall within 2 standard deviations. Well, if we add another 15, we'd get 130, and that would be 70. So 95% of the people who take an IQ test will score between a 70 and a 130. And then 99.7%, or almost all the values, will fall within 3 standard deviations, 145, and this would be 55, right? Okay. So that's what a normal model. Now, something that's important, remember, this is a model and it's an approximation. So if does that mean that 68% of all people will fall within 85 and 115? No, approximately 68% will fall there. Okay, it's a good approximation of what will happen, but it's not an exact science. Okay, so the standard or normal model has a mean of 0 and a standard deviation of 1. So the way that we do a standard normal model is we do it like this. And the reason that we do it is we want to compare. So, for instance, for men's height, I believe that the men have a normal model of a mean of 69 inches with a standard deviation of 3. And women, it's something like, I think it's 64 and standard deviation of 2.5. So if I was to say, well, if what's more uncommon, a man that's 6 feet tall, or a woman that's let's see, would that be 5? Let's say 5'10". Yeah. So a man that's 6 feet tall is 1 standard deviation above normal, 69 plus 3. A woman who's 5'10" would be 2 standard deviations above normal. Well, what's more uncommon? Well, the woman is. A 5'10" woman is more uncommon than a 6 foot tall man, because that's farther from the mean. That's 2 standard deviations from the mean. So it allows us to compare unlike things on a normal model. You can compare SAT scores with ACT scores, as long as you know the mean and the standard deviation. Okay, so it allows us to compare things and put things on the same scale. That's the whole point of using a standard normal model. It allows us to put things on the same scale for comparison. Okay? So the normal model is determined by the mean and the standard deviation. We use the Greek letters mu and sigma because it is a model. It does not come from actual data. Sigma and mu are the parameters, okay, that specify the model. So this is mu, and this is mu plus 1 sigma, mu plus 2 sigmas, mu plus 3 sigmas, mu minus sigma, mu minus 2 sigmas, mu minus 3 sigmas. Okay, parameters are things that apply to populations. So we have all these kids, okay, that all pay, I don't know, all this money, and they all pay and they take this thing called the SAT. Alright, so all these kids, you might have some kids that are not happy about taking the SAT. Okay, so and, the SAT testing service is very happy to collect your money, so they all pay, and they put all these happy faces in there, and there's some happy faces and some sad faces, and all these kids, all the kids that ever took the SAT. And what they do is they come up and they compute these things. So they say, okay, well, what's the mean for the SAT math? And the mean for the SAT math is what we're going to call mu. And that's, mu is the mean for every kid that took SAT math. And that's around 500. And then they do the standard deviation for all kids that take the SAT math, and we're going to call that sigma. And that's around 100. So what we get is we get the SAT math, all the kids who've ever taken the SAT math, the mean is about 500 and the standard deviation is 100. Now, these things in parameters, again, are models. In most cases, these are not knowable. For instance, I gave you the height of all males. Well, how can we get the height of all males? Do we have a day where we go and measure every single male that's walking around planet Earth? Well, no, we can't do that. So again, this is a model, this is an approximation. Okay, a lot of times parameters are unknowable. And that's going to be one of the things, or one of the tenets of this course, in that we use statistics to try to tell us things about parameters. Well, what are statistics? Well, from these populations, we take these things called samples, and in these samples, we get a mean. We call that x bar. It's not mu. And we get a thing called the standard deviation, which we call S of x, which I went over last chapter. And all samples from our population will not be the same, but they will be good approximations of what's happening in our population. And what we're trying to do is we're trying to approximate what these parameters are. And again, in our normal model, we're assuming that everything's nice, and we know all the parameters. But again, just keep in mind that these are our models, and they are good approximations of what is going on. Okay, so as we move forward. So the larger sigma is, the more spread out the normal model appears. Okay, so let's say that in this normal model we have a standard deviation of 100 in both, and this one has a standard deviation of 5. So this is 105, 110, 115, and this would be 95, 90, and 85. But let's say that this one has a standard deviation of 50. So this would be 150, 200, and 250, and this would be 50 and 0 and negative 50. Okay. So now this inflection point is about concavity, and basically concavity, if I was to draw a curve, we would say that this part of the curve right here is concave down because the water would pour out of it, and this part of the curve is concave up. Well, there's a point in this curve, let's say it's right about there, where the concavity changes. It goes from concave down right here to concave up over here. That's an inflection point. And this normal model, you could see, is concave down in here but concave up over here, and that inflection point occurs one standard deviation from the mean. So one standard deviation on either side of the mean. Okay. So back to our SAT math scores, we have a mean of 500 and a standard deviation of 100, so we would write that as n. That means normal model, capital N. The first thing is the mean, the second thing is the standard deviation. So that means we have a mean of 500 and a standard deviation of 100. So that would look like this: 600, 700, 800, and then 400, 300, and 200. I don't think you can get less than 200 on the map, and you cannot get more than 800. So that would include all students who take the SAT math score. So in fact, that 99.7% would actually be 100%. So suppose a group of 50 BMHS students take the math SAT exam. Which of the following would be true? Well, the scores of these students will be normally distributed. Well, is that true for our 50 students? Well, no, it's not. The entire population of students who take it would be normally distributed, but let's say we have a really good class. So let's say that a lot of them score 600 and a few of them score 500 and a few could actually be skewed left. So the sample from our school does not have to follow the actual model itself. So that's false. The histogram for those scores will be symmetric. Well, now I just showed it wouldn't have to be. and go back and answer the first question a little bit more profoundly. There's no guarantee that this, from our school, 68% of our students are going to score between 600 and 400. Or there's no guarantee that 95% will score between 300 and 700. Or that 99.7% will score here. We may have different percentages. So not only might we get a distribution that's not unimodal and symmetric, but the distribution itself may not be normally distributed as our model indicates. So 1 and 2 are false. 95% of the scores will be within 2 standard deviations of the mean. Well, again, there's no guarantee whatever our mean is that 95% of the scores will be within 2 standard deviation of the mean. Okay? 95% of our scores should be within 2 standard deviation of mean, but there's no guarantee that it will be. So all 3 of those are false. Alright, so to estimate the mean and standard deviation here, this is something that's typical within the AP exam. So, if I was to look at this, let's see, this is going up, this looks like it's going up by 10. This is 80, 90, 100, 110, 120. Now again, we are estimating. Okay, so again, this this model is unimodal and symmetric. So, you know, what's your estimate for the mean? Well, it's somewhere probably going to be between 80 and 90. Okay, well, you say, well, it's 85. Well, it could be 85. It doesn't have to be exactly 85. Okay, remember, it's going to be in here somewhere, probably. It's going to be in somewhere in this vicinity, but there's no guarantee it's going to be right in the middle. Okay, so we're gonna say it's around 85. Now the standard deviation. Now again, we're using this to create a model. I always like to go out a little bit further than what the model goes, so I'm going to go out to like 140-ish, and I'm going to take this out to 30-ish. So if I was to take the mean and I was to go 1, 2, 3 standard deviations to the right, and then 1, 2, 3 standard deviations to the left, in effect I've created 1, 2, 3, 4, 5, 6 areas. So what I can do to estimate that is simply say, okay, 140 minus 30 divided by 6, and that would give me 110 divided by 6. An approximation for that would be, I don't know, somewhere around 18.3. Another way to think about it is, look, you went from 85 and you're going up to like 140. Well, if I go from 85 to 140, I have 3 standard deviations. So if I do 140 minus 85 and I divide that by 3, I get around 18.3. So my estimate for the standard deviation is somewhere around 18.3. You could say 18.5 if you wanted. Again, it's an estimate. Okay. So let's take this next one. First thing I always like to do is say, okay, what am I counting by? Well, that's 30, 35, 40, 45. Draw my normal model. I like to extend my distribution a little bit, so that's 50. This is 5. So what's your estimate for the mean? 27, 28. Could be 26, could be 29. Okay, I'm going to say around 27 and a half. Okay. Now again, if I go, here's my mean, I divide this 1, 2, 3 standard deviations, 1, 2, 3 standard deviations. That means there's 6 standard deviations between the min and the max. So I do 50 minus 5 over 6. and that's 45 divided by 6, and that's around 7.5. Okay, so that works out. Go ahead and give this one a whirl, and then click it back on. Alright, so the 300, 400, 500, 600, 700, 900. Okay, so there we go. I'm going to draw my normal model, make that 1,000, make that 100. And so there you go. So what's your estimate for the mean? Most of you said probably somewhere around 550-ish. Okay. Standard deviation, I do 1,000 minus 100, so that's 900 divided by 6. So the standard deviation is somewhere around 150-ish. Okay. So that's how you estimate the mean and the standard deviation. Alright, so z-scores. Now we're dealing with z-scores, we're dealing with normal models, and what we have to keep in mind is we know two things. Okay, we know that this thing is going to look, it's unimodal and symmetric, and we know the mean, mu, and we know the standard deviation, and we know that it follows this model where 68% of the people or subjects are going to be within one standard deviation of mean, 95 within 2, and 99.7 within 3. So z-scores are a way for us. Z-scores are simply, all they want are telling us are how many standard deviations are we away from the mean. That's all they're telling us. So remember when we talked about standard normal models? That's what we're dealing with here. We're dealing with standard normal models. Okay? So they allow us to compare normal data. Puts data on the same scale. The z-score tells us how many standard deviations something is from the mean. Very simple. You take the score, subtract the mean, and divide by the standard deviation. Okay? So we have a SAT math score. 500 is mu and 100 is the standard deviation. Well, what's a z-score of 600? Well, 600 is 100 points above the mean. Well, 100 points above the mean is one standard deviation above the mean. Okay, so think of it this way. Let's just draw the SAT math. 500, 600, 700, 800, 400, 300, 200. So where's 600? It's right there. Person scored one standard deviation above the mean. That's what a z-score is. So z is 600 minus the mean over the standard deviation. 600 minus 500 is 100. 100 divided by 100 is 1. What does this mean? It means that this person scored one standard deviation above the mean. Okay? How about 450? Well, 450 is right in between 400 and 500. Well, we know that 400 is one standard deviation below the mean. So what's 450? Well, 450 is a half a standard deviation below the mean. How do we get that? We do 450 minus the mean over the standard deviation. Negative 50 over 100. Negative 0.5. What does that mean? This person scored 0.5 standard deviations below the mean. Okay? What is more common, the 500 or 650? Well, who scored farther from the mean? What's farther from the mean? One standard deviation above or 0.5 below? Okay. Okay. Well, the answer is the person who scored the 600. The 600 is more uncommon because it is farther from the mean. Alright, so here's the actual SAT scores down here. So here's the 600 and here's the 450. The 600 is farther from the mean. Standardized, I would do this. There's the 600, one standard deviation above the mean. Here's the 450, negative 1.5 standard deviations below the mean. Well, what's more uncommon? The line that's farther from the mean. Alright, so now we have a comparison problem. We got the height of males. Males have a normal model with a height of 70 inches with a standard deviation of 3 inches, and females have are described by a normal model with a mean of 65 inches and a standard deviation of 2.5 inches. So males would look like this. Okay. And females would look like this. Okay. So what's more unlikely, a 7-foot male or a 4-foot female? Well, how do we, let's see, a 7-foot male, that's 84 inches. So let's see, that would be, let's say, how many standard deviations? Well, that's what we use a z-score. So I'm going to do the z-score of the male. So 84 inches minus the mean over the standard deviation is 14 over 3. It's almost 5 standard deviations from the mean, which is 4.67 standard deviations. Now a 4-foot female, that's 48 inches, and that's 48 minus 65 over 2.5. So 48 minus 65 is negative 17 over 2.5, and that's actually 6.8 standard deviations. Okay, well, both of them are highly unlikely when you consider that 99.7% of males are between 61 and 79 inches, and 99.7% of females are between 57.5 and 72.5 inches. So these are both very unlikely to be walking around, 7-foot male or 4-foot female. But what's farther from the mean? Well, this female, the 4-foot female, is more unlikely than the 7-foot male, though both of them are highly unlikely. Alright, so guidelines for normal models. Since 95% of individuals fall within 2 standard deviation to mean, anything within 2 standard deviations is generally considered acceptable. Anything more than 2 standard deviation to mean is generally a cause for concern. Alright, think of it this way. I'm going to do a normal model, and for IQ scores. Intellectual IQ scores are normally modeled with a mean of 100 and a standard deviation of 15. So when we do IQ scores, we say, okay, I'm just going to look at this end of it for now. Anybody that has above a 2 standard deviations is considered to be highly intelligent. Okay, I think if you get up above 145, then this is considered what? A genius, right? So that's anybody that scores within more than 3 standard deviations. But our threshold is going to be 2 standard deviations. Since 95% of individuals would score between 70 and 85, then anything that's outside of that 2 standard deviations, since this is 95%, would be considered highly unlikely to happen. So when we're looking at things in terms of z-scores and standard deviations, 2 standard deviations is generally where we're going to draw the line. We're going to say, okay, anything above that is not likely to happen. Okay, so I think in our last module we looked at heights of males, and that was males had a mean height of 70 inches and a standard deviation of 3. Well, think about the school right now. Subtract 2 standard deviations from 70 and you get 64. And you add 2 standard deviations to 70 and you're looking at 76. So 64 inches is 5 foot 4 inches, and 76 inches is 6 foot 4 inches. Now, are 95% of the people walking around our school between 5 foot 4 and 6 foot 4? Probably, in terms of males. Now, how many people do you know that are above 6 foot 4? Probably not many. Okay, and how many males do you know that are below 5 foot 4? Well, probably not too many of them either. As a matter of fact, 95% of males are not going to be below 5 foot 4 or more than 6 foot 4, and the same thing with females. Okay, if we do 65 and the 2.5, then that would put us between 60 and 70 inches. Okay, well, that's 5 foot tall, and that's 5 foot 10. So 95% of the females that you probably know are between 5 foot tall and 5 foot 10. There aren't too many females walking around that are more than 5 foot 10 or less than 5 feet tall. Okay, though you may know some, the majority of them are not. Okay. So here's a practice problem. Here's a woman's shoe size. So we got to sketch each one of these and describe it using the empirical rule. So for females, the average shoe size is 8.25, and we would add 1.15, so that would be 9.4, 10.55, and 11.7. And we subtract 8.25 minus 1.15, we get 7.1, and then 5.95, and then 4.8. Okay, and then let's calculate for males. Males are a little bit easier. So it's 11.5, 13, 14.5, and 8.5, 7, and 5.5. Okay, now if you're asked to do this, be very careful. Okay, remember that these are models and these are approximations, and we have to, when we describe things using our 68, 95, and 99.7 rule, we have to take that into account. So I'm going to go through males because it's a little bit easier, but you would do the same thing for females. And how I would answer this question is I would say approximately 68% of all males have a shoe size between 8.5 and 11.5. And then I would say approximately 95% of males have a shoe size between 7 and 13. As a matter of fact, let me rephrase those. I would say the model predicts that approximately 68% of all males will have a shoe size between 8.5 and 11.5. And then I would say the model predicts that approximately 95% of all males will have a shoe size between 7 and 13. And then I would say the model predicts that approximately 99.7% of all males will have a shoe size between 5.5 and 14.5. And you would do the same thing here. The model predicts that 68% of all females have the model predicts that approximately 68% of all females have a shoe size between 7.1 and 9.4, and then 95%, and then 99.7. Do not say, if you're asked this question, 68% of all females have a shoe size between 7.1 and 9.4. That's not true. Okay, it's a model and it's an approximation. So you must note that in your explanation. Okay, so a woman that wears a size 10, we would do 10 minus 8.25 over 1.15, and that's 1.75 divided by 1.15, and that's approximately 1.52 standard deviations above the mean. And the z-score for males is 8 minus 10 over 1.5. That's negative 2 divided by 1.5 is negative 1.33 standard deviations below the mean. So what's more uncommon? Well, the female here is more uncommon. Okay, she's farther from the mean. Though neither one are highly unlikely because they're both within 2 standard deviations of the mean. So, though the woman who wears the size 10 is less likely than the man who wears size 8 because she's farther from the mean. Okay. Alright, so using normal models to find unknowns. So back to our female data. So we need 2 commands in our calculator, and I'll show you where these are. Go to second distribution, and you'll come up with this model right here. This distribution is this second vars button. And you'll get this, we need norm CDF. And on your calculator it's normal CDF, and the one right below it inverse norm. And norm CDF finds the percent in area, and inverse norm finds the z-score from a percentile. Okay. So we're given a problem, and there's one thing we are always going to do. We're going to draw a picture, and it just has to be a rough sketch, but here's what we know about females. The mean height is 65 inches. How do I know that? That's right there. 2.5 standard deviation is my standard deviation, so that's approximately 5'10" is 70 inches. So that's going to be 2 standard deviations above the mean. Taller. Taller means we're going to shade this way. Okay? So here's what we're going to do. Go into the screen here, go up to norm CDF. How do you do that? Second vars, you get this screen again. Not norm PDF, norm CDF. And you're going to come up with this menu. Now our lower bound of our shaded region, it starts at 70 and it goes to infinity. I'm going to represent infinity by putting 1,000 there. My mean is 65 and my standard deviation is 2.5. And if I push enter, I get approximately 0.023. And that means that approximately 2.3% of females who are walking around are 5'10" or taller, or probably around 2 out of every 100 females. How about 5'5" and 5'8"? Well, 5'5" is 65 inches, and 5'8" is 68 inches. So that's shaded, this shaded region right here. So now I go to norm CDF. My lower bound now is 65, my upper bound is 68. Look at my shaded region, it goes from 65 to 68. My mean and standard deviation are the same. And I get approximately 0.385. So about 38.5% of all females walking around are between 5'5" and 5'8". Shorter than 5'2". Well, 60 inches is 5 foot, so 62 inches is 5'2". And I'm going to shade to the left. Now be careful here. We go to norm CDF. What's my lower bound? Well, it's negative infinity. So I'm going to put negative 1,000. What's my upper bound? Well, it goes up to 62. My mean and standard deviation don't change. So it's about 11.5%. Okay. Now, did you notice that all of these started with find the height, or find the percent of, find the percent of, find the percent of? In all those cases where you're finding a percent, you're going to use norm CDF. When you're finding something that is specific, not a percent, you're going to use inverse norm. I need to know the height that represents the 90th percent of all females. Well, the 90th percent is going to be up here. I need to figure this out, so I'm going to go to inverse norm. And the area is the 90th percentile. My mean is 65 and my standard deviation is 2.5. And it's going to be about 68.2 inches. Top 25% of all females. So the top 25% is right there. Well, where does that begin? It begins at the 75th percentile. Okay, so I go to inverse norm, and I want to know the 75th percentile. Now, and it's about 66.7 inches. Or taller. Top 25% is 66.7 inches or taller. Now the IQR is going to be from the 25th percentile to the 75th percentile. Well, we already know what the 75th percentile is. It's 66.7 inches. So now I need to figure out what the 25th percentile is. So I need 0.25 and 63.3. So that's Q3, that's Q1. What do we do to get IQR? We subtract them. 66.7 minus 63.3. 3.4 inches. So that means 50% of all females, or the middle 50% of all females, are between 63.3 inches and 66.7 inches. Okay. So here's SAT math again. So find the percent. When we find the percent, what are we doing? Norm CDF. Okay. So there's 500. Where's 650? It's there. or above. Shade to the right. Norm CDF. What's the lower? It's 650. The upper is 1,000. I might go 10,000 this time, because I'm estimating infinity. I can even put 100,000. It doesn't matter. My mean is 500. My standard deviation is 100. So about 6.7% of all people who take the math SAT will get 650 or above. 420 and 620. Now again, this is a rough sketch. You might say, well, Mr. O'Neill, this is actually only 80 away and that's 120 away, yet they look like they're equidistant. I know. Again, it's a rough sketch. You don't get credit for drawing a good sketch. You get credit for answering the question. So we are going to go to norm CDF because we're finding the percent. The lower bound is 420. The upper bound is 620. Mean is 500. The standard deviation is 100. So it's about approximately 67.3% of all students will get between 420 and 620. Now find the score. So now when we're doing find the score, it's inverse norm. Top 10%. Where's the top 10%? It's here. It's all these kids right there. Well, what percentile does that begin at? It begins at the 90th percentile. So we want to look at the 90th percentile and above. So let's look at inverse norm. I want to look at the 90th percentile with a mean of 500 and a standard deviation of 100. And they would need approximately a 628. Again, this is an approximation. You say, well, you can't get a 628 in the SAT. I understand that. This is a model. We're just dealing with hypotheticals right now. They would actually need a 630. Find the score that represents the 15th percentile. Well, the 15th percentile is right there. So, inverse norm, 15th percentile. You need a 396. Oh, Mr. O'Neill, you can't get a 396. I understand that. You get about a 395. You can't even get a 395, I don't think. You need a 400. So if you got a 400, you'd be in the 15th percentile. Now the IQR. So we need the 75th percentile. And you need the 25th percentile. So let's find both of those. Inverse norm, 25th percentile, 433-ish. I'm just going to round this. And then this is 75th percentile. And what do you notice? 567. Well, what do you notice about those? This is 67 above, this is 67 below. They're equidistant from the mean. Well, this is 25% below. This is the 50th percentile. This is 50% above. So the IQR is simply 567 minus 433. It's 144. Alright, so now our next issue to tackle is we have to find both mu and sigma. So two SAT scores for two UConn students were as follows. Student A had 1250, which was at the 70th percentile. Well, if we look at a normal model, we know that the middle is the 50th percentile. So we know that the 70th percentile must be to the right of the mean. And that person had a 1250. And then this other student had an 1138, and that's at the 40th percentile. that's an 1138. Now, since we're given the percentile, we normally use inverse norm, right? So we go to inverse norm and we say, okay, this first one was the 40th percentile, but we don't know what mu is, so that's unknown. So I'm just going to put a 0 in there, and I'm going to put a standard deviation of 1, so I standardize it, and that means that's a negative 0.25. Well, what is that negative 0.25? That's a z-score. So it's negative 0.253. So boy, that 1138 is 0.253 standard deviations below the mean. Now I'm going to do the same thing with that 70th percentile. So that was 0.5244 standard deviations above the mean. And that's all we could do with that, because if we go to inverse norm, we really can't, we don't know what mu is and we don't know what sigma is, so that's the best we're going to do with it. So what I do know is that z equals some score minus the mean over the standard deviation. So negative 0.253 equals 1138 minus mu over the standard deviation, and I know the 0.5244 equals 1250 minus the mean over the standard deviation. So that must mean that negative 0.253, all I'm going to do is multiply by sigma, and this 0.5244 sigma equals 1250 minus mu. So now you have an equation with two unknown variables. So what do we do with them? Well, you learned in Algebra 2 that we put them on top of each other. So we got negative 0.253 sigma equals 1138 minus mu, and 0.5244 sigma equals 1250 minus mu. And then you have to get one of the variables to cancel. The easiest to get to cancel is mu, and you would change the sign, so you multiply this whole top equation by negative 1, and that'll change that to positive, and that'll change that to negative, and that'll change that to positive. So I got to add 0.253. I'm going to do that over here. 0.253 sigma plus 0.5244 sigma is 0.7774 sigma, and 1250 minus 1138 is 112, and I'm going to divide now by 0.7774. Divided by 0.7774, and I get that's 144. Then I got to take this and put it back into one of these two equations. So I'll put it into, let's see, 0.253. That was a negative 0.253 times 144 equals 1138 minus mu. So negative 0.253 times 144 is negative 36.432 equals 1138 minus mu. Subtract 1138, we get 1174.4 equals negative mu. So mu is around 1174. And that's how we would do that kind of problem. Consider the fuel economy of all cars can be modeled by a normal model of 24 miles per gallon with a standard deviation of 6. An ecology group is for a national goal calling for no more than 10% of all cars to be under 20 miles per gallon. So we have this, and that's 24 miles per gallon. And no more than 10% of all cars, so this would be 10%, would be under 20 miles per gallon. So what they want to do now is they want us to change our average fuel efficiency. So here's what's going to happen. We got to go to inverse norm, and 10% is a z-score of negative 1.282, and so negative 1.282 would equal 20 minus some new average over 6. And now we just solve this equation. We would do 6 times negative 1.282, and that's about 7.7. And then we would subtract 20 from that, and we get negative mu is negative 27.7. So mu is about 27.7 miles per gallon. So the new average has to be 27.7 instead of 24. Car companies argue that they cannot raise the average that much, but they believe that they can only get 26. What standard deviation will allow them? So now it's the same problem. The new mean would be 26, but there's sigma. So we would get negative 1.282 equal sigma equals negative 6. And if we divide negative 6 by negative 1.282, we get about 4.7. Okay. So what changes in the fuel economy cars would achieving that standard deviation bring about? What are the advantages and disadvantages? Well, if you go from a standard deviation of 6 to a standard deviation of 4.7, there would be less variation in fuel economy. So what's good about that? Well, you'd have a lot less cars with really bad fuel economy, but that's the positive. But the drawback is you would have less cars with really good fuel economy. Okay, so that's the advantage and disadvantage. Alright, so the last thing we're going to look at is assessing normality. And when we're doing that, the first thing we're going to do is we're going to examine the shape of a histogram. A normal model is symmetric. Unimodal about the mean, and roughly symmetric. So it's going to be unimodal and roughly symmetric. Compare the mean and the median. In a normal model, they are approximately equal. Verify that the 68, 95, 99.7 rule holds. And lastly is construct a normal probability plot. So what we're going to do here is I'm going to take this data set and I put it in L1, and I'm going to go to stat plot, and I'm going to go to plot 1 on, and I'm going to turn on histogram, for L1, and I'm going to go to zoom 9, and I have an error mismatch. So let's take a look what's going on here. The frequency should be empty. And let's try this again. And it doesn't like that either, so let's put a 1 in there. Okay. Alright, so that's what the histogram looks like, right? So our histogram would look like this. And this is 50, 60, 70, 80, 90, and this is 100. Okay. And then this normal probability plot. So this is unimodal, and it's symmetric. So this normal probability plot is this last one here that's right below the histogram. And my data list is L1, my data axis is X, and I'm just going to mark it, and then I'm going to push zoom 9, and you see there that my normal probability plot is fairly straight. Now the normal probability plot will be straight when this is roughly unimodal and symmetric. Okay, now let's take this second data set. So what does it look like? Well, it looks like this, and that's the normal probability plot, so it's pretty straight. So let's take, I put the second data list in L2, should be 50, and I'm going to change that back to a histogram, and I'm going to change it to L2, and I'm going to push zoom 9, and my data now is skewed. So I have a histogram that looks like that. Okay. And that would be 50, 60, 70, 80, 90, and then 100. Okay. And then if I go to my normal probability plot, we go to the one right below histogram, that one right there. We go to zoom 9. You see that it's curved. Okay, so it looks like this. So it's actually going like that, whereas this one went straight. Okay. So what I've done on the next page is I showed you here's a histogram of a distribution that's nearly normal. You look at it like that and you say, wow, that's roughly unimodal and symmetric. And here's what the normal probability plot looks like. Then you have a skew distribution right here, and then what happens is the normal probability plot comes out curved. So in looking at data, this is a way for us to assess normality, okay, which we'll have to do in future chapters.